We are about to start a series of lessons on chemical reactions. So it's important for us to go over some basics of chemical reactions and give you a bit of a foundation before we start the specific 5 different types of reactions. I like the phrase that is on this slide where it says, formulas show chemistry at a standstill. We've just finished a series of lessons on nomenclature. We understand how to come up with the chemical formulas of compounds, but it's just a standalone item. But a chemical reaction or a chemical equation shows chemistry in action. And so we can get a lot of information out of a chemical reaction and understand exactly what is happening to our reactants and our products. Chemical equations show the reactants which enter into a reaction. They also show the products that get formed by the reaction, and they also indicate the amounts of each substance that is used. We understand that a chemical equation would be balanced to satisfy the law of conservation of mass. We can see this here in this example of the production of water. But we also know that those coefficients that are in front of our substances, and if there's a coefficient of 1, we don't enter it in, okay? So there would be a 1 there, but we don't write it in. They indicate the amounts of each of your reactants and products that either get used up or formed. So we know in this reaction, and this is how we would read it, that 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. And that is how you would read a chemical equation. Remember that this arrow here is not an equals sign. We never say the word equals when we are reading a reaction. There are 2 important principles to remember related to chemical reactions, and we have mentioned a few of these already when we have talked about the law of conservation of mass. Every chemical compound has a formula which cannot be altered. So when we did our lesson on conservation of mass, I did go over some examples of balancing where you balance with coefficients rather than altering the chemical formula. Okay, there's specific ways we come up with those formulas. We have to follow those rules. A chemical reaction must also account for every atom that is used. And this is the application of the law of conservation of mass. So we have to have balanced reactions each and every time we are dealing with them in chemistry. And in our next unit, you will see how important that becomes when we start to apply mathematical principles to our reactions. Some things to remember about writing chemical equations. So we've already touched on the diatomic gases, and they're not all gases. I know bromine and iodine are liquids and solids, but what is true for each of those, because they are nonpolar molecules, they sublimate or they evaporate very quickly into the gas state. But you have to be aware of those diatomic elements, so those Hofbrinkel elements, as you write these chemical equations. And if you forget to put in a subscript of 2, you may not be able to balance your reaction and you get a ripple effect from there. A reminder that this arrow that we use between reactants and products means yields, or sometimes we use the word forms. Either one is fine. You never ever say the word equals. Okay, that is not an equal sign. And this is not a mathematical equation like you would see in math class. This is a chemical equation. A small delta symbol, okay, so a triangle above the arrow shows that heat has been added. Many times in our chemical reactions, we add heat, either to speed up the reaction or because we need an outside source of it to get bonds to be broken and then electrons to be rearranged. So when we put a triangle above the arrow, it tells everybody that heat has been added. Some reactions have double arrows, and then that shows that the reaction is reversible. You are not going to see any of those in grade 11 chemistry, but you certainly will if you decide to take 4U chemistry. When we balance our chemical reactions to satisfy the law of conservation of mass, we always do this by placing coefficients, okay, in front of the formulas. And we never, ever alter a chemical formula. So again, we've heard this before, but it is a really important point to make and to repeat. Number 6, states of reactants and products are indicated within the reaction to provide extra information. In grade 10 science, you probably didn't deal with states too much. But now that we start to talk about reactions, states of matter become very, very important to give us extra information. And we apply a state of matter to every single reactant and product in a reaction. So we assume that you know the basic ones. So here's solid, here's liquid, here's gas. But the other state of matter that you can have, and is very common in chemistry, is AQ. This stands for the term aqueous, and this implies, or it tells anybody that has a background in chemistry, that you have dissolved that substance in water. Okay, aqueous means it's a dissolved solution. You have to know those and you have to apply them. Number 7, some products are unstable and then they'll break down or decompose as soon as they are produced in a reaction. So there are several compounds that do this, but in our course, you need to know these two right here. Okay, so there will be a time where you are dealing with chemical reactions, so maybe a double displacement reaction, and you form carbonic acid. Okay, so you write the word or the formula for carbonic acid on a product side, and then you have to know that immediately, as soon as that compound gets formed, it will decompose immediately into 2 other products. And this is where, carbonic acid is formed when you do good old baking soda and vinegar, for example. You form the carbonic acid, but immediately it breaks down into water and CO2. And this is why you always see gas bubbles produced when you mix vinegar and baking soda together. Another example is sulfurous acid over here. So sulfurous acid as well, if you created that in a chemical reaction, it is up to you to realize that it also spontaneously decomposes into water and sulfur dioxide.